This is a screenshot of what appears to be a social media video, possibly from TikTok or Instagram Reels. The image displays a list titled Jetstream in Canon Formulas, which contains 14 distinct mathematical and computational expressions. The formulas are a diverse collection, drawing from various advanced fields. Cryptography, formulas involving SHA 3 to 512 hashing, 1, 2, and 0 knowledge proofs, 14. Information theory, expressions for Kullback-Leibler divergence, $D underscore KL $5, and min entropy $H underscore min $6. Physics and quantum mechanics, the Heisenberg uncertainty principle delta X CDO to delta P G E Queech bar / $2.13, a formula related to the Planck-Einstein relation 12, and a stochastic differential equation 7. Abstract mathematics, concepts from category theory 9, topology / geometry 4, and analysis, such as the definition of a contraction mapping 8. The text at the bottom states, this is the canon, the closed, sealed set of Jetstream in formulas 1 through 14. Link to jetstream.github.io. The social media handle at .all.lux is also visible on the right side of the screen.
Okay, and if we applied to LLM, what conclusions, pros, cons, improvements can be made?
Excellent question. This set of 14 formulas presents a fascinating and highly ambitious conceptual framework for an AI system, likely an LLM, that goes far beyond current architectures like the Transformer. If we were to apply these principles to the design of an LLM, here's an analysis of the conclusions, pros, cons, and potential improvements. Overall conclusion, this is not an architecture, it's a constitutional framework for an AI. It attempts to build a model grounded in principles of cryptographic verification, physical reality, information theory, and mathematical logic. The goal seems to be to create an LLM that is not just a powerful statistical pattern matcher, but a verifiable, efficient, and logically consistent reasoning engine. It aims to solve fundamental problems in modern AI: hallucination, opacity, black box problem, and data provenance. Analysis of application to an LLM. Let's break down what each group of formulas would imply for an LLM's operation. Formulas 1 to 14, cryptographic integrity and verifiability. H underscore I equals SHA 3 to 512. Capsule underscore hash equals SHA 3 to 512. Pi equals proof. Application. Every piece of data the LLM processes, every inference it makes, and every update to its state would be cryptographically hashed and chained together like a blockchain. The model could then use zero-knowledge proofs, ZKPs, to prove it generated an output based on specific inputs and internal states, without revealing proprietary data. Conclusion. This creates an LLM with an immutable audit trail. You could mathematically verify the provenance of any statement it makes. Formulas 5, 6. Information theoretic learning. S underscore T plus 1 equals S underscore T, D underscore KL, H underscore min equals log 2, max BR. Application. The LLM's learning process would be explicitly driven by principles of minimizing surprise, Kullback-Leibler divergence, similar to a Bayesian brain. It would also constantly measure its own uncertainty, min entropy, about its knowledge and predictions. Conclusion. This would be an LLM that knows what it doesn't know. Its updates would be efficient, and it could explicitly state its confidence level, potentially refusing to answer when uncertainty is too high. Formulas 12, 13. Physically grounded computation. E is greater than or equal to C omega, delta x square, delta P is greater than or equal to C/2. Application. These are not meant to be simulated, but to act as regularizers or constraints on the model's computation. It implies that the model's operations have an energy cost, and there's a fundamental uncertainty in its internal states. Conclusion. This could lead to extremely efficient models that avoid wasteful computation, naturally balancing precision and performance, much like a biological brain. Formulas 8, 9, 10. Logically consistent reasoning. T of x minus ty is less than or equal to c. Y. F nu hollow bullet mu equals F nu hollow bullet F mu. ID underscore A, comma B equals path underscore A, comma B. Application. This is the most abstract and powerful part. The LLM's internal thought processes would be governed by formal mathematical structures. Contraction mapping. 8. Guarantees that an iterative reasoning process will always converge to a stable, single answer. Functor 9. Ensures that the model preserves structural relationships when mapping knowledge between different internal representations, e.g., from language to a conceptual graph. Identity type 10. Provides a profoundly deep way to handle equality and analogy, going beyond A equals B. It understands that two things can be the same in different ways. Conclusion. This would be an LLM that is incapable of contradicting itself. Its reasoning would be robust, consistent, and capable of sophisticated analogies. Pros. Potential benefits. 1. Trust and verifiability. The cryptographic backbone would allow for mathematical proof of a model's claims and data sources, drastically increasing trust. 2. Reduced hallucination. The combination of information theoretic uncertainty, H underscore min, and logical consistency, functors, identity types, would make it far less likely for the model to generate confident nonsense. It would know the limits of its knowledge. 3. Data provenance.